crystal defects. So in this part 3, we are going to discuss about the stoichiometric crystal defects, or known as intrinsic defects, and second one is the non-stoichiometric crystal defects, or known as extrinsic defects. So here, alright, so what is stoichiometric crystal defects or intrinsic defects? This is where the defects, okay, have enough number of ion per every cation in balance the to balance the charges. So here, okay, we have two types of stoichiometric crystal defects. They are the Schottky defects and also Frenkel defects. So and for the second one, we have non-stoichiometric crystal defects, or known as extrinsic defects. Okay, this is where the defects have the numbers of anions and cations are unequal. Okay, and we have two kind of situation in order for these extrinsic defects to form. Okay, for the first one is oxidizing the cation, and second one is the filling up a vacant anion site using electrons. So for the first one is for the intrinsic defects or stoichiometric defects. Okay, first one is the Schottky defect. This was found by Walter H. Schottky, a German scientist. Okay, alright. So for these defects, okay, we need to have a vacant cation site and a vacant anion site. Okay, so in this example here, okay, here for this one, alright, this is arrangement of sodium chloride. Okay, so here in this sodium chloride, one sodium and one chloride here are missing. Okay, so you need to make sure that we have a balanced number of missing cation and also anions. Okay, alright. So in this case, okay, take anions and cations and place them on a surface of equal numbers. Okay, so make sure they are balanced. Okay, and then it can be it may be randomly distributed, but usually they tend to cluster because of the oppositely charged vacancies. Okay, and also because of the size. Okay, and this is for the Schottky defects. Okay, it is actually very usable or very important with alkali halides. Okay, and at room temperature, okay, about 10 to the power of 15 pairs vacant in sodium chloride. So 1 milligram sample has about 10,000 Schottky defects. Okay, so the charge neutrality is maintained within the crystal, and there is no charge in the composition because we have vacancies of equal number of cation and also anion, so they can balance the positive and also negative. So that's all for the Schottky defects. Okay, next we go to the Frenkel defects. This is where the Yakov Frenkel, he is a Russian physicist. Okay, found this defect. Okay, so in this case, okay, we have unequal number of cation and also anion, and as you know, cation is smaller and it can get displaced to interstitial voids. Okay, alright. For example, in gold argentum iodide here, and also calcium fluoride. Okay, so because of the size of cations, okay, are smaller than the anion, so it can move around. Okay, for this diagram here, okay, an atom here, this is cation, moving into an interstitial and a space, okay, moving into a space side and creating a vacancies, okay, creating a vacancy. Alright, so because of the small size here, okay, it can move around and create a vacancy. Alright, so other than that, here, okay, we have this is argentum chloride, or okay, here this is argentum chloride or silver chloride, where the argentum, okay, get or move around, okay, and cram itself between this chloride and also this argentum, okay. So for this this argentum is actually surrounded by 4 chloride, okay, 1 2 3 4 4 chlorides to stabilize, in order to stabilize this defect, okay. Alright, so for this kind of Frenkel defects, okay, usually we are going to have the tendency for vacancy and interstitial to form nearby the pair, and also the stoichiometric defects where the vacancies usually refer to the interstitials, okay. Alright, and then Frenkel defects are common in fluoride structures, okay. For example, calcium fluoride and also zirconium oxide, and also argentum or silver chloride. Okay guys, so this is the summary of the Frenkel defect and also Schottky defect, okay. So for the first one, this is a pair of a set of cation and also anion vacancies, okay. And this one is where we have the Frenkel defect, okay. A cation here, okay, is out of a place, it should be here, and then this cation move around and sit itself here. And last but not least, for this part is the non-stoichiometric crystal defects or extrinsic defects, where the factors are actually from the outside, okay. For the first one is oxidizing the cation. It happens to the metal where the metal can have a few different oxidation states. For example, iron, okay. So iron can be positive 2 or positive 3 here, okay. So in this diagram, one iron 2 cation is missing. So what happened here? The charge imbalance, okay, and this charge imbalance can be corrected by increasing the oxidation number of the iron. From iron 2, it will become iron 3, okay. So this is where we have one missing iron 2 ion, okay, creates a charge imbalance in the lattice. So what happened here, this iron 2, from the iron 2, it start to oxidize itself to become iron 3 here and also here, in order to balance back the lattice, okay. Alright, so the charge imbalance is corrected by losing 2 electrons, okay, by losing 2 electrons from here and also here, and creating 2 iron 3 ions from the 2 iron 2 ions. So as a result, there are more sulfides, okay, compared to the iron 2 ions in the crystals, resulting a non-stoichiometricity, okay. Alright, so here, other than that, the non-stoichiometric compounds can be happen for in copper oxide and also copper sulfide and also iron oxide. And second one, other than oxidizing the cation, is the filling up a vacant anion using, or vacant anion site using electrons. So we balance the imbalance charge happen here using electrons, okay. For example, here this is a sodium chloride lattice, okay, reacts with sodium vapor, resulting the loss of chloride ions, okay. We have a missing chloride here, okay. So in order to repair or in order to correct the imbalance. So what happened here, okay, a trapped electron is used to balance the charges. Okay, so everything is back to the normal. Alright, so that's all for the part 3. I hope you guys enjoy the video, and please don't forget to like, comment and also subscribe to my YouTube channel. So I will see you guys in part 4.